All right, well, welcome to session 3 of Water Treatment 1. In this presentation, we're going to be looking at some coagulation dosage calculations. Um, and we're also going to have a little bit of a recap on last week's presentation in case maybe some of you didn't attend that one. So without any further ado, here we go. So here's our quick review from last week's presentation on coagulation, flocculation, and sedimentation. For today's presentation, we're going to go ahead and define coagulation as the process by which small particles are combined to form larger aggregates. Um, and it's also important to consider the objective of coagulation, and it's to condition particles so they can be readily removed in subsequent treatment processes. Um, And basically, the point of that portion of the objective is just to emphasize that we're not trying to remove any particles during the coagulation step. We're just trying to eliminate their negative charges so that they can stick together and form settleable or filterable flock in subsequent steps of the treatment process. Um, it's also important to mention that removing the particles reduces the waterborne pathogens, disinfection byproduct precursors, and color-causing compounds. And for those of you who attended last week's session, you'll remember that for surface water or subpart H systems, we're looking at a multi-barrier approach. And so the coagulation, flocculation, and sedimentation along with the disinfection is providing the multi-barriers to ensure that we produce safe drinking water that's free of pathogens and microorganisms. Well, so here's some of the key concepts that we're going to be working with today. Uh, Coagulant, sometimes you'll hear them called the coagulation chemical or a coagulant aid, is a chemical which is added to the water to help small particles stick together for later removal. Um, and colloidal material, which is generally the small particles that we're targeting, present in raw surface water have negative charges. Therefore, one critical step in the coagulation process is to neutralize these charges. Again, you probably remember if you attended last week's presentation, but the primary coagulants are going to have strong positive charges to help neutralize those negative charges. Um, there are some polymers that are either also negatively charged or have no charge themselves. Those can be fed as a coagulant aid, but they can't be fed as a primary coagulant. State and federal regulations require the addition of a primary coagulant to surface water sources to ensure microbial removal credit. Because one of our objectives is to neutralize the negative charge, the primary coagulant must have a positive charge. Cationic, as if you remember, cationic is positively charged, anionic is negatively charged, and non-ionic is neutrally or no charge. So only a cationic polymer can be fed as a primary coagulant. There are many coagulants on the market with various properties. Um, for the remainder of this presentation, we're going to focus on some of the most common coagulants: aluminum sulfate or alum, ferric sulfate, and ferric chloride. Um, These are the most common coagulants in Michigan, although we do have some plants that feed cationic polymer as a primary coagulant, and there are some complex forms of aluminum that can also be used as a primary coagulant. Um, it's really a case-by-case basis on what coagulant is best for each specific plant, and there can be a lot of variables that go into that, and Also, whether you use a coagulant aid in addition to your primary coagulant, that can be something that's done seasonally or year round. It's really has to be taken on a case by case basis. So today we're just going to focus on the three most common coagulants, and we're not going to really consider coagulant aids that might be fed in addition to these primary coagulants. So one of the most common coagulants is aluminum sulfate, more commonly referred to as alum. It comes in two forms, dry and liquid. Dry alum is pale green to white in color and is available in powdered and ground forms. It's sometimes referred to as filter alum, and it can contain varying amounts of water. Chemically, dry alum is expressed as Al2, two aluminums, SO4, that's our sulfate, there's three of them, by H2O. And we have an X in the H2O, and that represents the proportion of water of hydration. It's typically 14, but it can vary from 11 to 18. For a lot of our calculations today, we're going to be using 14. Um, on a molecular weight basis, dry alum is usually 17% aluminum oxide and 9% aluminum. We're going to get into how to calculate that in some of our practice problems. Uh, Liquid alum is a clear to light green to light yellow solution. It's heavier than water with a specific gravity of approximately 1.3. You'll remember for specific gravity, water has a specific gravity of 1, so 1.3 is going to be heavier. The strength of liquid alum can be estimated using a hydrometer or a Balm scale. You'll see Balm scales for acid too. Alum products with higher strength would have higher degrees of Balm. So we're going to take a quick look at some of the product data sheets for alum. Um, these include some important information that you may need for some of your calculations. Um, you can see your dry alum equivalent. We're going to be using that in some of today's problems. The molecular weight of dry alum, this is very handy, although I suppose if you work with alum frequently, you're going to have it memorized, but it's a nice quick reference so you don't have to figure it out from the start each time, but we will during today's presentation. Um, you can also see here, it'll help you understand what phase the alum is going to be in based on the temperature and the concentration. Whoops, did we miss one? Okay. Aluminum sulfate, dry versus liquid alum. Um, you can see here we've kind of got two columns, one for dry alum, one for liquid. We're going to go through a few of the properties here. Percent by weight, 9% aluminum in dry alum, 4.4 in liquid. Percent by weight aluminum oxide, 17% for dry alum and 18.3 for liquid. And then percent by weight of alum, this is for dry equivalent. So you can see this is 49%. And of course, there isn't one for dry alum because this is for figuring out the equivalent dry alum for a liquid alum dose. But I also just like to spend a second to look at this 49%. It's almost half. And if you go back up and look at these other properties that we were just reviewing, you'll see 4.4, just about half of 9, 8.3, just about half of 17. And this can be kind of a helpful tool when you're working problems, especially if you're studying for an exam, just as sort of a gut check on your calculations. You know that it should be about half or 49% when you're going from liquid alum or dry alum to liquid alum, and about double if you're going the other way. So just something to keep in the back of your mind when you're working problems. Okay, the iron-based coagulants that we're going to look at today are ferric sulfate and ferric chloride. Ferric sulfate is a reddish-brown liquid, and it's typically available as a 60% strength product. It's a cationic coagulant and flocculant suitable for municipal water treatment for the removal of turbidity, color, and disinfection byproduct precursors. It is also used for wastewater treatment processes such as phosphorus control and sludge conditioning, compaction, and volume reduction. Liquid ferric chloride is a dark maroon liquid. It is used in both municipal and industrial water treatment. Ferric chloride is effective for the removal of turbidity, color, and disinfection byproduct precursors. Because they are iron-based products, ferric sulfate and ferric chloride may also be effective for arsenic removal. Okay, so now we're going to take a quick look at a product data sheet for some ferric sulfate. You can see here they have a few different strengths available for this product, so you'll have to be aware of which one you're looking at. But here they actually show you the ferric ion, which ultimately this is where our positive charges are coming from, and depending on what you're trying to calculate, this can be a very important variable. Also, something important on this sheet that wasn't really highlighted on the other is in this certification section. And if you see here, it says ferric chloride is ANSI/NSF standard 60 certified for use in public water treatment and also meets or exceeds all AWWA standards. This is important. Sometimes it's on the product sheet, sometimes you'll see it on the container itself, but it's important to always make sure that you have documentation and that it's clear that whatever product you're feeding to the water has the NSF standard 60 certification. So sometimes you might have the same chemical, but it doesn't have NSF 60 certification. That can't be fed to the water supply. You need to make sure anything you're adding to the water has an NSF standard 60 certification. Here's a few of our math references. We won't be circling back to this because they're mostly called out on the individual slides, but these are some of the information we're going to be using on our practice problems today. So we'll jump right in with the first practice problem, and this is going to be a weight percent calculation. And the question is, what is the equivalent weight of aluminum in aluminum oxide? So we've got the aluminum oxide formula there, 2 aluminums and 3 oxygens. Equivalent weight is the same as weight percent, and that is the percent weight of aluminum in a sample of aluminum oxide. So the way that we're going to be able to solve this is we're going to calculate our weight of aluminum, and then we're going to go ahead and divide that by the weight of the aluminum oxide. And as we discussed, we've got 2 aluminums, Al2, that's what this indicates, and we've got 3 oxygens, O3. So back on our reference page, we listed the molecular weight of these 2 elements. Aluminum is 27 milligrams per millimole, and oxygen is 16 milligrams per millimole. So to figure out what the weight of aluminum is, we have Al2O3, so 2 aluminums, 2 times 27 is 54, O3, 3 oxygens times 16 milligrams per millimole is 48 milligrams per millimole. So the total weight is 54 plus 48, which is 102 milligrams per millimole. And now we'll divide the weight of the aluminum by the weight of the aluminum oxide, and we'll multiply it times 100 to get our percent. 54 divided by 102 times 100 is 52.9% aluminum in aluminum oxide. So now we're going to take a look at equivalent weight of, so the question is, what is the equivalent weight of aluminum in alum? That's what we have there. And you'll notice here we have our 14 H2O. Those are our waters of hydration. Again, we discussed those can vary. So, if you're preparing for a test again, that can vary, but typically you're going to see 14 used in all of the calculations and problems. The equivalent weight of aluminum means the percentage of aluminum by weight in a sample of dry aluminum sulfate. So, similar to the other problem, we're going to have to first figure out what the weight of each one of the elements in this compound is. So, we still only have two aluminums, Al2. And this gets maybe a little tricky if you haven't spent a lot of time doing chemistry, but basically this SO4 is your sulfate, and you're going to notice that it's in parentheses. And anytime you see that, basically there's going to be a little subscript number outside of the parentheses, and you're going to need to multiply whatever's inside the parentheses by this subscript. So there are 3 sulfates in here. We have 2 aluminums and 3 SO4s, and then 14 H2Os. In order to figure out the weight of each element, we're going to have to break this down a little bit further. Aluminum sulfate consists of aluminum, sulfur, and oxygen. And then, of course, we have our waters of hydration over here, so we're also going to have hydrogen atoms. So how many of each atom are there? We already discussed we have 2 aluminum. That's pretty clear, Al2. This is a little tricky, maybe if you haven't spent a lot of time doing it, but there is no subscript next to this sulfur here. So basically that means it's just 1. So 3 times 1 is 3. We have 3 sulfur. Inside the parentheses, we have 4 oxygens. 3 times 4 is 12. But we also have some additional oxygens over here. We have 14 waters. So 14 times 1 is 14. Plus we had our 12. So that's going to get us 26 total for oxygen. And then hydrogen, we've got 14 waters, and there's 2 hydrogen in each water. So we're looking at 28 hydrogens. So that's the first step you want to do, is just take your time and figure out how many of each element you have. And like I said, it can be a little tricky at first until you kind of get your head around how to expand these multiplications with the parentheses. Okay, so we don't have to memorize this stuff. We're not going to flip back to our reference page, but we have it available there. And so the molecular weight of aluminum is 27, sulfur is 32, oxygen is 16, and hydrogen is 1. Now we're going to take the expansion that we did and how we figured out how many of each element we have in our formula. We have 2 aluminum, 2 times 27 is 54. Sulfur, we had 3 of them from the previous slide. 3 times 32 is 96. Oxygen, between the aluminum sulfate and the 14 H2O, we had 26 atoms. 26 times 16 is 416. And then we had 28 atoms of hydrogen, and they are 1 milligram per millimole, so we have 28 milligrams per millimole of hydrogen. So the weight of the alum plus the waters of hydration is all of the values that we just calculated on the previous slide added together. This is going to give us our total weight, 594 milligrams per millimole. And as I mentioned, when we looked at that alum product data sheet, this was listed right at the top. So if you don't have it memorized and you needed to do a quick check and you have the product data sheet available, you can always pop back and take a look at that and not necessarily have to go through all the calculations that we just did. Also, though, like I said, I think if you're working with alum, you're probably going to have that number in your head anyways. So the percent weight is going to be whichever one of these elements we're interested in, or could potentially be, a grouping of elements. If we were interested in our sulfate, we could do SO4 instead. But in this case, we're looking for aluminum. So we're going to take our weight of aluminum and we're going to divide it by the total weight and multiply it times 100. So we have two aluminums. That's 54 milligrams per millimole. And our total was 594 milligrams per millimole times 100, which comes out to be 9.09% aluminum. So that's important because, again, this is where our charge neutralization is coming from, is from this aluminum ion. So we know that we have 9.09% aluminum ion. Okay, we're going to take a look at some dosage conversions. And for this one, we're going to be looking at converting a dosage of 1 milligram per liter aluminum ion to an equivalent dose as milligram per liter of aluminum or aluminum oxide in this case. So the molecular weight of aluminum oxide is we have 2 aluminum, Al2, and 3 oxygen. 2 times 27 is 54. 3 times 16 is 48 for a total of 102 milligram per millimole. So here was our original dose, 1 milligram per liter aluminum ion. We're going to divide that by the number of milligrams per millimole that are aluminum in aluminum oxide, and then we're going to multiply it by the total weight of the aluminum oxide. And you can see, again, if you're taking a test or you're taking this course in preparation for a test, sometimes you can use the units to help you, and it's always important to make sure that all of the units are canceling out so you end up in the right units for your answer. So here we can see milligrams of aluminum are canceling out. We can see that our millimole of aluminum oxides are canceling out. So we're left in units of milligrams per liter. And the answer is 1.89 milligrams per liter aluminum oxide. And again, if you are preparing for an exam, you can revisit the question or the problem statement here and see that we are trying to convert 1 milligram per liter of aluminum ion to an equivalent dose of aluminum oxide in milligrams per liter. So it's always a good idea to make sure that our answer comes out in the units that the problem asked it for. And we can verify that right here. Okay, for this next problem, we're going to be looking to convert a dose of 11.01 milligrams per liter as alum to an equivalent dose of aluminum ion. We're not going to go through all this math again, and probably by the end of this presentation, you will have 594 milligrams per millimole memorized, but here's how it breaks down. Again, now we're going to look, we have 11.01 milligrams alum per liter. And now we're going to go times 1 millimole of alum per 594 milligrams of alum. That's what we have right here. It's the alum has been placed in both the numerator and the denominator, which can be maybe a little bit confusing, but ultimately we're looking at milligrams per millimole here. We've inverted it, so we end up with our millimoles on top and our milligrams on the bottom. And we know now that there are 54 milligrams of aluminum ion in every millimole of alum. So we go 11.1 milligrams divided by 594 milligrams times 54 milligrams, which brings us to our final dosage of 1 milligram per liter aluminum ion. And they don't show it on this slide, but you can see how our units would cancel each other out. We get rid of milligrams of alum, milligrams of alum. We get rid of millimoles of alum, millimoles of alum, and we'd be left in milligrams per liter. It's always handy to make sure that the units make sense. It's a good indicator that maybe you have made a mistake or got things flipped around. If you can't verify that your units have canceled, then you end up in the correct units for your answers. So just a little bit of a general math strategy, I suppose. Okay, so now we're going to take our answer from the previous problem here, and they want us to convert 1.89 milligram per liter of aluminum oxide to milligrams per liter of alum. Okay, so here we go again, deja vu, right? Here's how we get to our 594 milligrams per millimole. We know what our original dose was. We have 1.89 milligrams per liter as aluminum oxide. So they kind of skipped this step in this slide, but we've done it several times in the previous problems. And we can just take a quick look here to verify, but the total weight of aluminum oxide is going to be 2 aluminums. So we have our 54. And then we have 3 oxygens. 3 times 16 is going to be 48. 48 plus 54 is 102 milligrams of aluminum oxide. So that's where this 102 comes from. And then, of course, we have our alum weight, which we've seen on almost every slide now. So we divide our original dose that they provided us of aluminum oxide by this molecular weight of aluminum oxide, and then we multiply it times the total weight of alum, and we're back where we began at 11.01 milligrams per liter alum. Quick check on the units, cancel out our milligrams per liter aluminum oxide, these two, and we're going to cancel out our millimoles with these two, and we're going to be left in units of milligrams of alum per liter, which is exactly what we're looking for. Okay, so here we go, jumping into a little bit more complicated problem. See if we can put some of the steps we've learned in the previous problems to work here. 200 pounds of alum are added to 3 million gallons of water. We've got a multi-part problem here. Part A, what is the dosage rate in ppm of alum? Part B, what is the dosage in ppm of aluminum ion if the alum is dry alum with 9.09% available aluminum? And the third part of the problem is going to be what is the dosage in ppm of aluminum ion if the alum is liquid alum with 4.4% available aluminum? All right, well, let's start with part A. What is the dosage rate in ppm of alum? So this is probably going to look familiar to some of you, but ppm is equivalent roughly to the pounds of chemical per million pounds of water. So in our problem statement, they told us that we have 3 million gallons of water. So here we have our 3 million gallons per day. Back on our reference sheet or reference slide at the before we started the problems, this information would have been provided. So you wouldn't necessarily have to have this memorized, but I guarantee you if you do enough of these problems, you're going to have it memorized. And that is that 1 gallon of water weighs 8.34 pounds. So again, following our units here, we've got 3 million gallons times 8.34 pounds per gallon. Our gallons are going to cancel out, and we're going to end up with 25.02 million pounds of water. So we just discussed here that ppm is the pounds of chemical over the million pounds of water. We know that we have 200 pounds of alum, and we just calculated our million pounds of H2O. So if we go 200 pounds of alum divided by 25.02 million pounds of H2O, we're going to end up with an answer of 8 ppm, or milligrams per liter of alum. And it can be a little confusing, but a ppm is the same as a milligram per liter. So that can make it maybe a little bit trickier to follow your units all the time, but just something that you're going to have to keep in mind, because sometimes you'll see them presented in ppm and sometimes you'll see them presented in milligram per liter. All right, moving on to part B. What is the dosage in ppm as aluminum if the alum is dry alum with 9.09% available aluminum? You could calculate the available aluminum. However, you could also look back at the product data sheet and it'll most likely tell you what percentage available aluminum is in the product. In this case, we're given the percentage, so that's handy. Again, the formula for dry alum, we've got our Al2SO4 and our 14 waters. We've done we did the weight percent calculation as one of the first practice problems, and you'll probably remember we divided the weight of the aluminum by the total weight of the alum, and we did come up with our 9.09. Whoops. And from part A of the problem, we know that our dosing rate is 8 milligrams per liter, or you could say 8 ppm. It's kind of interesting how they flip back and forth. This is good practice because you might see this on some exams, or if you're working in the plant, you might see on some data sheets it's milligrams per liter, and maybe there's some calibration sheets or something in the plant for your feed pumps that are in ppm. So just have to kind of keep in mind that those are pretty much interchangeable. So ppm as aluminum ion is going to be your ppm of alum times your percent weight of aluminum ion. And that makes sense because we're looking at our total weight times the percentage that's aluminum ion, and that's what we're interested in. So we have 8 ppm times, and here you'll notice that they've just taken the percentage and converted it to a decimal. So all you're going to do is divide it by 100 and move this decimal up 2 spots. 1, 2, got to add a 0. 0.0909, which comes out to 0.72 ppm as aluminum ion. The final step of this problem: what is the dosage in ppm as aluminum if the alum is liquid alum with 4.4% available aluminum? So they provide a little background here, and we've kind of touched on this a little bit, but liquid alum comes from the manufacturer with a specified dry alum equivalent. Typically, this value is 48.5%, which means 1 pound of liquid alum is the equivalent of 0.485 pounds of dry alum, about half. You'll remember we kind of touched on that in one of the earlier slides. It's about half. Therefore, if dry alum is 9.09% aluminum by weight, liquid alum is 9.09 times 0.485, which is 4.4% alum by weight. You might also see that presented on the product data sheets like we were looking at the start of the presentation. But if you don't have that, there is a way to calculate it as well. Okay, so from part A, we will remember that we are dosing at 8 milligrams per liter, and we are interested in the aluminum ion, which is going to be our ppm as alum times our percent weight as aluminum ion. 8 milligrams per liter. Again, we converted our 4.4% to a decimal. Just have to move this 2 places. 1, 2, which is going to get us our 0.044 for a final answer of 0.35 ppm as aluminum ion. And I'm going to see if I can flip back here. So we were at 0.72 as dry alum, and then we're at 0.35 as liquid alum. Again, just as sort of a double check or gut check, as I would call it, you can see that that's about half, right? We were at 0.72 and now we're at 0.35. So that just gives you a little extra confidence that you didn't miss a step or didn't have an error in your calculation. All right, moving on to our next problem. A water treatment plant treats 10 million gallons per day, MGD. You're going to see that a lot, and utilizes alum. If the plant is using dry commercial alum, how many pounds of alum must be applied daily to achieve an application of 0.5 ppm as aluminum ion? So even though this one doesn't clearly break it out into multiple parts like the previous problem did, there are going to be multiple steps to this problem. And we already did several of them in the last problem, so we'll kind of move over those pretty quickly. Again, we've got our 594 milligram per millimole, and then we can look here, we're trying to figure out the percent aluminum, which we just did in the previous problem, is our 54 divided by our total, which is going to get us an answer of 0.0909. Or if you'd like to see that as a percentage, you can multiply it times 100, move this decimal 2 places, 9.09%. Here we are. Step 1 is to find the equivalent dose of alum. From the past practice problem, we know that the ppm as alum times the weight percent of aluminum ion is the ppm as aluminum ion. So what do we know in this problem? We already know the weight percentage as aluminum ion. We just figured that out. That's our 0.0909. And we know what our dosing is as aluminum ion, 0.5 ppm. So now we're going to rearrange this formula. And basically, if you cross the equal sign, you're going to have to, if you're in the numerator on one side and you're cross, you're going to end up on the denominator on the other. In this case, we're trying to solve for ppm of alum, so it stays put. And we're going to have to move our weight percent of aluminum ion to the other side of the equation. So here we go. We move our 0.0909 over. It was in the numerator when it was on this side, so now it's in the denominator. So you divide 0.5 ppm by 0.0909, and you have your dose in terms of alum, which is 5.5 ppm. Number 2 continued. We've got another step here. Step 2 is to find the total pounds of alum used daily. So you might remember this from one of our previous problems as well, but we said the ppm equals the pounds of chemical divided by 1,000,000 pounds of water. In the problem statement, it told us that we had 10 mgd or 10 million gallons of water per day. So again, we need to get this in terms of million pounds of water. And on your reference sheet, there will be the weight of water, which is 8.3 pounds of water per gallon. We multiply this out, 10 times 8.34. We're just going to move this decimal one place, which is going to give us 83.4 million pounds of water per day. We have our dose. Again, you can kind of go between ppm and milligrams per liter. So we have 5.5 milligrams per liter alum, and we know how many total million pounds of water we're going to treat in a day. So we're going to rearrange this formula. We're solving for the pounds of alum. It stays put. When we move this over, it was on the denominator, or bottom of the equation on this side. So it's going to be on the numerator on this side, which means it's going to be multiplication. So we have, again, we're flipping back and forth between ppm and milligrams per liter. 5.5 ppm times 83.4 million pounds of H2O is going to get us 458.7 pounds of alum. That's how much they will be using in a day if they treat 10 million gallons and they have a target dose of 5.5 milligrams per liter as alum. All right, practice problem number 3. If liquid alum contains 8.3% aluminum oxide and each gallon weighs 10.7 pounds, how many gallons are used with a dosage of 1 milligram per liter as aluminum ion? Assume the plant flow is 5 million gallons per day. Okay, this should start to look a little bit more familiar, hopefully, as we keep going, but we've got our 5 million gallons per day, and we know that, well, we either know or we look at our reference sheet to see that water weighs 8.34 pounds per gallon. So 5 million gallons times 8.3 pounds of water per gallon. You'll see our units are going to cancel out. We're trying to get to million pounds, so the gallons are going to cancel. Leaves us with 41.7 million pounds of water per day. Okay, so step 2 is to solve for the pounds of aluminum ion. In the problem statement, they told us that we had 1 ppm as aluminum ion. And we know how many pounds of water we have. We just calculated that in a previous step. So again, we're going to rearrange. We want to solve for pounds of aluminum ion, so it's going to stay put. And this 41.7 is going to move over to the other side of the equation. It's going to move from the denominator to the numerator, and we're going to be multiplying. So pounds of aluminum ion equals 1 ppm times 41.7 million pounds of H2O per day equals 41.7 pounds per day of aluminum. And this is where it can get a little bit tricky maybe to keep track of your units, but this is parts per million, so it's basically 1 over a million. And this is 41.7 million pounds per day. So the millions are going to cancel out, and that's how you're going to be left with just 41.7 pounds per day of aluminum ion. All right, moving on to the third part of this problem, we need to solve for the pounds of aluminum oxide. So we know that, and we've done this in a few of the problems now, but for aluminum oxide is 52.9% aluminum by weight. And that, looking at our formula, aluminum oxide is Al2O3. So aluminum is going to be 54 because you have 2 times 27, and the oxygen is going to be 3 times 16, which is 48. So that's how you get to the 52.9% as aluminum by weight. We've done it a few times, so it isn't worked out on the sheet, but don't want to skip that. So in order to solve for this, the pounds of aluminum oxide times the weight percent of aluminum equals the pounds of aluminum. So what we know here is we know the weight percent of aluminum. We were given that, but we could have calculated it, is 52.9%. We're going to need to convert that into a decimal, so it shifts the decimal 2 places back, which gets us 0.529. And we also know from our previous calculation on the last slide that we had 41.7 pounds of aluminum. So we're going to rearrange the terms to solve for pounds of aluminum, and it's going to be 41.7 divided by 0.529, which gets us a total of 78.83 pounds of aluminum. And something you can think to yourself to feel confident in your calculation is that we had 52.9% by aluminum, and we wanted to get to aluminum oxide. So right away, we know the weight should go up, and we know that it should be somewhere close to double because the weight percent is 52.9%. So anyways, these are just some things I like to think about when I'm doing these calculations. It's easy to get your units messed up or skip a step somewhere, and it's nice to have these sort of high level checks to make sure your answer is in the range it should be. Okay, step 4, solve for the pounds of liquid alum required to give 78.81 pounds of aluminum oxide. And the hint here is the problem stated that liquid alum contains 8.3% aluminum oxide. This is the weight percentage of aluminum oxide. Very good. Well, it's been a while since we looked at the problem statement, so I guess that is a pretty helpful hint. We're going to go back to our original formula here, pounds of a liquid alum times the weight percent of aluminum oxide equals the pounds of aluminum oxide. So what do we know? We know our weight percent and we know our pounds of aluminum oxide, and we're trying to solve for pounds of liquid alum. So we're going to rearrange by moving this weight percent to the other side of the equation. It's going to go from the numerator to the denominator when we do that. So we're going to be dividing 78.83 pounds of aluminum oxide by the weight percent. Again, this is the 8.3 converted to a decimal, 0.083, which is going to give us a final answer of 949.73 pounds of liquid alum. Step 5, solve for gallons of liquid alum required. Okay, so we discussed this a little bit earlier that each gallon of alum weighs 10.7 pounds. Again, you could go back to your reference sheet perhaps, or to the product data sheet to get that information if it wasn't given to you. But we know what our pounds of liquid alum is, and we know that 1 gallon weighs 10.7 pounds. We're going to follow our units here again. We're trying to get to gallons. So our pounds are going to cancel each other out, and we're going to end up with 88.74 gallons of liquid alum. Okay, I think, let me see. Yep, we got time for another one. Okay. What is the alum dosage in milligrams per liter of aluminum ion if a water treatment plant treats a source water with an average flow of 700 gallons per minute? A total weight of 150 pounds of dry alum is used during a 24-hour period. Dry alum contains 9.09% aluminum ion by weight. You see this too, here they're showing it as aluminum ion with the +3 charge designation. And here we're seeing it just as the elemental symbol for aluminum, but don't let that trip you up. First step is to find the million pounds of water. So we're going at 700 gallons of water per minute. And so we're going to go from minutes to hours to days here. And the way we're going to do that is we're going to say, well, there's 60 minutes in an hour, cancels out your minutes, 24 hours per day, hours cancel out. So then we're left in our time unit being day. We were in gallons of water, and we know 8.34 pounds of water per gallon. Gallons are going to cancel out, and we're going to be left in pounds of H2O. So that's 8,406,720 pounds. It's a lot of digits. We like to be working in millions of pounds. So basically, there's 6 decimal places in a million. So you're going to end up going 1, 2, 3, 4, 5, 6. And that's going to give you 8.407 million pounds of water. That's going to be more useful for us in the next steps. Whoops. Step 2, solve for ppm of alum and for the concentration of aluminum ion. So ppm is going to be the pounds of chemical over million pounds of water. We've used that one a few times today. So we know it's 150 pounds of dry alum divided by 8.407 million pounds of H2O, and that's going to get us to be 17.84 ppm, or you could say milligrams per liter of alum. And again, we already converted this to millions of pounds, and so the pounds cancel each other out, and then we end up in ppm because this is actually millions of pounds. It's this capital M designates. So ppm as aluminum times the weight percent as aluminum ion is going to give us the ppm as aluminum ion. And we've got 17.84 milligrams per liter as aluminum times our 9.09. Of course, this had to be converted to a decimal, just moving it 2 places up. 0.0909 gives us a final answer of 1.62 milligrams per liter as aluminum ion.
Hey, Andrew, you can keep going to 9:35 and we'll take a 5-minute break then.
Okay, thank you. I was wondering.
Yep.
All right, here, this will be our last one probably. How many pounds per day of liquid alum are used if the flow rate is 12.7 million gallons per day and the dosage is 8.25 milligrams per liter of alum? The dry alum percent equivalent is 48%. Step 1 is to find the million pounds of water per day. So we've got this time they gave it to us in millions of gallons per day. So we went ahead and split that up so you can see millions of gallon, and then day is in our denominator. We're going to multiply that times our 8.34 pounds of water per gallon, which is going to give us 105.92 million pounds of water per day. So now we're going to solve for the pounds of alum using the ppm equation. So ppm of alum equals the pounds of chemical versus the millions of pounds of water. So we have 8.25 ppm of dry alum times 105.92 million pounds of water per day equals 873.84 pounds of dry alum per day. And again, this is just us rearranging this formula. We want to solve for pounds of chemical. So millions of pounds of water comes across the other side of the equation. And when it does that, it moves from the denominator to the numerator. So that's how this formula was determined. Step 3, solve for the actual pounds of liquid alum, knowing the dry alum percent equivalent is 48%. So here they're going to show us the equation as it's typically presented. We've got our pounds as liquid alum times the dry alum equivalent equals the pounds of dry alum. Now we want to rearrange this equation because we're trying to solve for pounds of liquid alum. And so looking at, here's our pounds of liquid alum. That means we're going to have to move the dry alum equivalent to the other side of the equation. And when we do that, it's going to move from the numerator to the denominator. And we're going to have 873.83 pounds of dry alum divided by 48% converted to a decimal. 0.48 is going to be 1,820.48 pounds of liquid alum per day. We'll see if we can do a bonus test problem here. A 5-minute drawdown test result shows that 262 milliliters of alum is being injected. The alum weight is 10.46 pounds per gallon. If the plant is treating at 925 gallons per minute, what is the alum dosage in milligrams per liter? We're going to go a little quicker on this one. So we know that we have 925 GPM, gallons per minute. We're going to go ahead and convert to days. So 60 minutes in an hour, cancels the minutes, 24 hours in a day, gets rid of the hours. Now we're left in gallons per day, but we want to be in pounds of water. So it's 8.34 pounds per gallon for 11,108,880 pounds of water. So we know that we fed 262 milliliters of alum in 5 minutes. Again, we're going to get to days. So 60 minutes in an hour, 24 hours in a day, cancels our hours and our minutes. And then we're also going to go, this will be something you, at least for myself, you'll have to look back at your reference sheet, but 1 gallon equals 3,785.41 milliliters for 19.93 gallons of alum per day. Next step is to solve for the pounds of liquid alum and convert to milligrams per liter. We just calculated that this is how many gallons of alum we're feeding per day, and they told us in the problem statement it weighed 10.46 pounds per gallon. So that's 208.5 pounds of liquid alum per day. And of course, going back to our ppm equation, we take our pounds of chemical over our million pounds of water, 208.5 divided by 11.11 million pounds of water for a dose of 18.8 milligrams per liter of liquid alum. And I don't think we're going to make it any farther than that before 9:35 at least.
Awesome. Thanks, Andrew. Matt, if we could launch the next poll question if needed, and maybe we'll take a 5-minute break till 9:40.